Wow, really?
Okay, let's get started. Okay, guys, can we look up? So, sorry, just trying to fix this cable. There we go. Good. Okay, what we're looking at in this class is getting probabilities from tables. So we'll have a simple enough example, something not too difficult. Let's say we have a table like this. So let's split it up a bit. Here is male and female and smokers and non-smokers. So let's say we have 20, 10, 30, no, let's look at 60. Okay. Right, so this is a typical table you might see in some kind of biology paper. Doesn't have to be smoking and non-smoking. It could be something like treatment A, treatment B, something like this. It's a very common table, actually. Yeah, it's called a two-way table, I think. So we can add a little bit extra information to it, but we really have enough with the table the way it is at the moment. So, for example, I could extend this table to calculate the total number of smokers. What would that be? 50. And the total number of non-smokers? 70. And then total male is 30. And here? 90. Yeah? Now, I want you to notice that if you add the smokers and non-smokers, you get 120. And if you add the males and the females, you also get 120. So this number here will always match these two added and these two added, which really makes sense because this is the total if you break the group up as smokers and non-smokers, and this is the total if you break the group up into male and female. And so since everybody is one or the other, then you can't help but getting everybody both ways, either considering them as smokers and non-smokers or considering them as male and female. Okay. So what we need to practice is answering some questions using this table. So for example, if I said, what is the probability that a patient selected at random will be male? Well, we know what goes on the bottom, don't we? 120. And on the top? 30 males. So this is 3 over 12, or in other words, 1 over 4. So in this group, 25% are male. Okay, let's do another one. Let's make it a little bit harder. What is the probability that you'll get somebody who is a male and, now just because you said smoker to be different, I'll be non-smoker now. Just to keep you on your toes. What's he going to do next? Right, so what's the probability of getting a male and non-smoker here? Yeah, so that's 1 in 12. Okay. Let's say the probability of a smoker now.
70 over
50 over 120.
100. Okay.
Yeah? Okay. Now, the next one I'll write out in words, but it's the probability of getting a smoker from the males. So you're selecting at random from the men in the group. What's the probability to get a smoker? 20 over 30. Okay. Yeah, there are 30 men, that's the total, and 20 of those men are smokers. Now, does anybody know the symbol for this expression, this problem. No, not union, no. No, you write it like this. Smoker given that or from the males. Yeah, the vertical line. Yeah? Now let's see about this one now. Be careful with this one. Smoker or, this is the symbol for or, if you didn't know it. Smoker or male. Sorry, I don't think I said it, but I didn't write it down. This is the symbol for and, this is the symbol for or, and this is the symbol for given. Okay. So, well, what's on the bottom first? 120 is on the bottom.
80, 16.
No, actually, I can't see now. I need to zoom in a bit. Smoker or male? So, yeah.
Two fractions and then we add them together.
We could do it as two fractions, but right, what's on the top?
70, 80, 60.
I see the numbers.
60 over 120.
120.
Right, Carol, give me one answer. What's on the top?
50 plus 30.
60.
60.
Yes.
How did you get 60?
50 plus 10.
How did you get 50? Yeah, okay, right, yeah. So, yeah.
Okay, great.
Is it not 80?
So look, let's look. You want smoker or male. So if you get one of these people, you're fine. They're smokers, so they count. But there's 10 people here which also qualify. They're male,
60 then.
but they're not smokers. We don't care. Yeah.
We can use Venn diagram. It's clear.
Venn diagram is something we'll do. Venn diagram is something we'll do in a little bit. Yeah, not for this class, but you're right.
So it's just 50 over 120.
No, these three add together to make 60. 30, 20, 10. So yeah, it'll be, sorry, where are we at? 60 over 120, which is 1 over 2. Is that okay? Are you sure? Yeah? Let's do another one. So I'll give you 2 to calculate. So smoker, well actually I've asked you smokers among males already, so I'll just give you 1 to calculate. Smoker, oh did I not write this down? What was smoker among...
2/3.
Oh yeah, sorry, I just wrote the symbol down, yeah, 2/3, okay. Smokers among females?
30 over 90.
Well, yeah, you're only looking at the females, which are 90, and how many of them are smokers?
30.
Yeah, so this is 1 over 3. Is that okay, huh? Yes, yes. This is the not formula, like probability of A is 1 minus the probability of not A. Is this what you're thinking of? Yeah. What was I saying? Yeah, okay, so 1 over 3. So can you see that, well actually, you know, if you were collecting this data as part of some kind of a lab, some kind of paper you're writing, and you have these 2 results here, what would be a nice sentence, easy to read for the reader, that gives us gives us the relationship between the 2? Like you could say, oh, the probability of finding a smoker among the men is 2/3, and that of women among the women is 1/3. But there's a nice relationship between the 2 here. That's one word. So. Yeah, but there's no quantity in that. See, do you notice how the probability for smokers among men is twice that among women? It's 2/3 versus 1/3. Yeah. So you can get this very nice sentence here. You could say, men are twice as likely to smoke as women. You see, those two results can go together to make that statement. Men are twice as likely to smoke as women. So simply by being male in this study, it doubles your chances of being a smoker, because it's 2/3 versus 1/3. Okay? This is called a relative probability. What is the disadvantage with my sentence? If I said men are twice as likely to smoke, we don't know exactly how likely. Yeah. So it's a relative probability. So it tells us men are at higher risk than women, but it doesn't tell us what each one is. Okay. So like another example of that would be if you buy 10 lottery tickets. You all know lottery tickets?
Yes.
Yeah. If you buy 10 lottery tickets, you are 10 times more likely to win the lotto. Now that sounds great, but a very small number times 10 is still a very small number. Okay, so this is the problem with relative probabilities. You can't actually know how big they are. You're just comparing them to something else. This is something very, very important for all you guys, because most medical studies give probabilities as a relative. You know, like they would say something like, if you eat this food every day, you will be 3 times more likely to develop heart disease. You know, you've probably heard things like this before. So it seems to be all medical probabilities are always relative to like a healthy person or something. Yeah? Is this anything that Colin was talking about? No, but you've heard this type of language before. Yeah? Okay, good. So let's do another example. Let me see if I can find another one here for us to practice together.
You can put your book here.
No, I'm okay, thanks. Oh yeah, so there's, I'll give you an easy one to do, but then there's a very interesting medical one I want us to do together. But before I do that, I just want to make sure you've all got a handle on this. I'll make up one here. So we can have people drink coffee in the morning, tea, or neither. And we'll say male or female again. Okay, so we'll practice some of these. I'll give you a couple to calculate. So and you notice how you'll have to work out the totals yourself. So I want probability male, probability female and tea drinker, probability that the person drinks neither, or that they're male, and then finally the probability that they're a tea drinker given that they are female. So I just want to make sure you got a handle on this. Give me those 4 calculations, please. What's the total number of people here? 110, okay. Yeah. Yeah. Probability being male. 9/22 simplifies down to thank you. Female and tea drinkers, there's 5 of those. So that's 1/21 or something? 22? 1/22? Yeah? 5/110, isn't it? Yeah. Probability that they drink neither tea nor coffee,
45.
or they're male. Yeah, so it's all of these and this guy. Right? 40, 60, 85/110. So what's that? 17/22? Yeah. Tea drinkers, given that you know they're female. So among the females, probability of getting a tea drinker among the females would be 30/35, is that right? 5/6 then? 5/65? Oh, sorry, females, there's 65 of them. Thank you. So 1/13.
Yes.
Yeah. Yeah, we got that? Yeah. Now. Yeah. So, what we'll look at next, I think it's important and it's interesting because, like I said, everybody here, no, not yet, no. Everybody here is going to be doing either medicine or science or pharmacy or something like this, okay? So in your 4 or more years of study, you will have to be reading at some point statistics from a paper, getting information from a table. You might be reading about some research. You might have to write some paper. You can't avoid it, okay? So there's an important example down the bottom here, and the reason this is important is because it can show you that even with simple statistics, Ray, Dasha, come on. Pretend I'm telling you something important and useful for your future. Yeah, okay. Yeah, pretend. Oh. And also pretend you have a future. Okay. Too much imagination, huh? Okay, right. So look, we haven't done much statistics, probability. This is only our second hour, isn't it? But even with this little bit that we have, we can see that the situation is perhaps more complicated. So if we all look at number 7, we'll have a read of this together. The table below, you all have your book yet?
Which page?
90.
Yeah.
The table below is a record of 700 patients that were treated for kidney stones. Now, kidney stones come in 2 varieties, both small and large, to be precise. The patients were given one of 2 treatments. They were either given treatment A or treatment B. And here you can see the table below summarizing the outcome. So, for example, the people who got, how many people with small stones were successfully treated with treatment B? 2, 3, 4. And how many people with small stones were unsuccessfully treated? 36. Can you see? Small stones unsuccessfully treated with B. So, for example, we can see that the number of successful treatments with B versus the number of unsuccessful treatments is a big difference, isn't it? Yeah. So, let's answer these questions. You'll need your calculator. The first one is straightforward. You can, if you like, you can write the answer on the book because there's no real calculations here. First question, how many patients were treated with treatment A?
87.
Why is everyone saying 87? Yeah, exactly. Okay, so this is proving my point that these things aren't as easy as they seem.
350.
Yeah, 350. You added the 4 together. Yeah. Okay. Guys, what's all the chit chat? You're only adding numbers. You know how to add numbers, yeah. Right, so what do we get for the first one? 350. Okay, so write that down. Yeah. How many patients were treated with treatment B? Yeah, well, you know this because there were 700 altogether. So, this doesn't seem unusual, does it? It would seem only sensible that you split the patients equally among treatment A and treatment B. This seems like a sensible thing to do, right? Okay. Right, next one. C. What is the probability of being successfully treated with treatment A? So that is, you've received treatment A, and you want to know what's the probability to be successful.
59 over 50.
Well, can you tell me what it was before you simplified it? What's on the top?
59 over 50.
Okay. Yeah. 273 over 350. Yeah. Which is about 78% then.
Yep.
Okay, so can you write that down? Yep. Yeah. Okay. And part D now, you can see where this is going. What is the probability of being successfully treated with treatment B?
82%.
About 82%, is it?
82.
Yeah. What was it? 289 over 350, was it? Yeah? Okay, great. So at this point we can do some analysis, some assessment I should say. Part E, which treatment is more successful?
B.
Yeah, what did you say B was? 81-ish
82.
versus...
78.
Okay, so at this point it looks like treatment B is a more successful treatment than treatment A. Just a little bit though, but it's quite clear that B is ahead of A. Right? Okay. Next one now. So before I continue, please keep that in your mind, that B is more successful than A. Okay. Right. What is the probability of being successfully treated with treatment A if you have small kidney stones? So given that you have small kidney stones. 81 divided by... No. 81 divided by 87, isn't it?
Yeah.
There were 81 people successfully treated in A with small kidney stones, and in the A group there were 87 people treated with A.
93.
Is it?
Yeah.
Oh, 93%, yeah. 81 over 81 plus 6. Which is 87, thank you, yes.
We had to double check.
Yes, indeed. Okay, next question. What is the probability of being successfully treated with treatment B if you have small kidney stones? So that would be 234 over, what's that, 270? So what percent is that? 87. What is it? 87? Okay, come on. Well, anyways, we don't need to be exact because we can still answer the next question. Which treatment is more successful if you have small kidney stones? Treatment A. Okay, good. Right. Keep that in mind. All right. What is the probability of being successfully treated with treatment A if you have large kidney stones?
Yeah.
73%, is it? Yeah. What is the probability of being successfully treated with treatment B if you have large kidney stones?
69.
Okay, 68, 69. Yeah? Okay. Right. Which treatment is more successful if you have large kidney stones? Treatment A. Okay. Which treatment is more successful if you have small or large kidney stones? Well, we just said if we have small, which is better?
A.
And if we have large, which is better?
A.
So which is better?
A.
But what did we say earlier?
B. So it's
Yeah.
B.
What is going on?
Compare your answer for it.
So it's A. So it's B.
Aye, good, excellent.
Look at the answer. The answer says.
Wow. Doesn't make sense.
Yeah, it's A.
What is it?
B.
Well,
Yeah.
well, I suppose, guys, okay, so yeah, your mind's been blown now, right? I have made my point. Even with the simple level of probability that we have, we're in this ridiculous situation whereby, depending on how we did our calculations, we have a contradiction. Earlier, it looked like B was a better treatment, didn't it?
Yeah.
And that seemed pretty obvious. Then later, when we looked at the small group and the large group, in each of those groups, which was better? A. And you have to be in one of those groups, right? Doesn't matter which group you're in, because in both cases A is better for you. So now we have a complete contradiction that the other treatment is better. Okay? So I wonder if anybody has ever seen this problem before. Probably not, due to your surprise. But the question is, we still have to decide which is the better treatment, A or B. So, or I suppose I should say, rather, we have to decide of our two analysis, which was the correct analysis, what we did at the beginning or what we did at the end.
The end, because it's more detailed.
Yeah, that's nearly it, yeah. What exactly made it more detailed?
Large and
Yeah. The answer from the second analysis is the correct answer, because in that analysis we considered the effect of having small kidney stones or having large kidney stones. Whereas in the first group, we said nothing about whether you had small or large kidney stones. So, I don't know if you've ever... Oh no, I think you actually heard this word. I think Colin mentioned it in the lab report. Confounding variable?
Yes.
Yeah, what is your understanding of confounding variable?
Something.
A variable.
A variable.
Okay. Confounding variable is a variable which influences the other variables, and if you don't factor it in, you can get not only the wrong result, but sometimes, like here, the opposite result. Okay? A good example of a confounding variable is the example, if you were to look at ice cream sales and deaths by drowning, as there's more ice cream sales, there'll be more deaths by drowning. Now, obviously, that's ridiculous. It can't be that the more ice creams that are consumed, the more people that die from drowning, right? So there's some confounding variable which is interacting with those two variables. Can anyone think of what that variable might be? No, not that. Which one? No? Huh? Temperature. What happens when it's sunnier? More ice cream sales and more people swimming. Yeah. So, yeah, it makes sense now. So this is a good example of what's called a confounding variable. The kidney stone size is confounding here. It's making us not get the right picture because it's influencing the success of the treatments. Okay? So anyways, the point is, when you have more variables, you should analyze at this level, like I just did here. Okay? Right, so this is a very, very good biology example. This situation is called Simpson's paradox, where you get the opposite result than what you originally thought. Okay? Yeah. The other famous example of this is with Harvard. If you look at admission rate success among males and females for a place like Harvard, initially you would look at all the female applicants and all the male applicants, and you discover, like at the beginning, 81% or whatever of males got in and 78% of females got in, and you might say, well, clearly then there's some bias here. But then when you look at each department separately, like who got into Department A, who got into Department B, you get a different picture. You don't get this. And what's happening there is that you're not considering the choices men and women are making, which are different. So, for example, more women apply to medicine at Harvard than men, which is more difficult to get into to begin with. So it's making them seem like they're not getting admitted at the same rate. whereas more men applied to computer science, which has an easier admission route, so it made the overall men look like they were being more successful. Okay? So, you know, this is a complicated statistic. I want you to appreciate this when you're doing your further studies then. Okay? So we've done number 7. What I'd like you to do for the last few minutes then is 1 to 6, please. They're all very short, okay? 1 to 6. Yes. Huh? How could you have a question? No,